Hey everyone, welcome to This Explainer. I'm so pumped to dive into this with you today because we're looking at something absolutely mind-blowing. We're going to trace how the exact same math ancient scholars used to navigate the stars is literally the exact same tool we use today to make buildings accessible for everyone. Seriously, we're taking a trip from the vastness of the cosmos right down to the floor plan of a modern bedroom. Let's get into it.
So here's our game plan for This Explainer. We'll kick things off with the history of the grid, move on to mapping Regien's room, break down the Cartesian plane, talk about accessibility and distance, and finally, wrap up with a quick coordinate geometry quiz.
All right, Part 1, History of the Grid. Let's rewind a few thousand years and see where this whole grid-based thinking actually began.
The evolution of our modern coordinate system is just brilliant. It all started on a massive urban scale with the Sindhu-Saraswati civilization. They built these incredibly precise city streets, uniformly spaced about 10 meters apart. Talk about early city planning, right? Then, as mapping the Earth for navigation became absolutely crucial, the ancient Indian city of Ujjayani stepped up as the central longitude meridian. From there, scholars like Aryabhata totally revolutionized the math. He swapped out Greek chords for signs, creating celestial coordinates to pinpoint the exact positions of stars. Fast forward a bit, and the Arab scholar Al-Biruni perfected the astrolabe, a tool letting sailors use those very stars to find their coordinates out on the open ocean. Finally, in 1637, René Descartes took all these historical building blocks and formally tied it all together into the 2D plane. He proved that you could perfectly describe any geometric shape using algebraic equations and two perpendicular axes.
Actually, wait, let me back up a second, because we skipped one incredibly crucial step on that timeline. Around 628 CE, early Indian scholars, specifically Brahmagupta, formalized the concept of zero and negative numbers as actual algebraic entities. And wow. Think about that for a second. Without the invention of zero and negative numbers, the entire four-quadrant Cartesian plane we use today would be completely impossible. You literally couldn't go backwards or downwards on a map without his breakthrough.
Moving on to Part 2, Mapping Regien's room. Let's zoom in from ancient history to a super relatable, real-world story that shows exactly why this math matters to us right now.
So Regien is a student who is visually impaired, and his family recently moved to a new city. Now, navigating a totally unfamiliar layout can be a massive challenge, as you can imagine. But his sister, Shalini, who had actually just finished learning coordinate geometry in grade 9, had a total light bulb moment. She decided to use the exact same math we're talking about to build a tactile floor plan of his brand new room. By taking all that abstract math and turning it into a physical grid, Shalini completely empowered her brother. She used a really simple scale. 1 centimeter equals 1 foot. She pinned down key coordinate points to mark the corners of the furniture, like the bed, the wardrobe, the doors, and then connected those pins with thick wool. This tactile map let Regien safely feel the layout, the distances, and the exact directions of his new space with his own fingers, all before he even stepped foot inside.
All right, Part 3, the Cartesian plane explained. To really grasp how Shalini pulled this off, let's quickly review the mechanics of the 2D Cartesian coordinate system.
The absolute anchor of it all is the origin. You can think of the origin as the absolute starting line for every single measurement in two-dimensional space. It's that exact spot where the horizontal line, the x-axis, perfectly crosses the vertical line, the y-axis. And of course, its coordinates are always 0, 0. Now, when we're plotting points, we always use a pair of numbers written as x, y. And just as a quick refresher, the x-coordinate always tells you how far left or right to travel from that origin, while the y-coordinate tells you exactly how far up or down to go.
And hey, remember Brahmagupta's negative numbers? Thanks to him, these two intersecting axes divide our flat plane into 4 distinct sections, or quadrants. This is what lets us map locations in all 4 directions. If both numbers are positive, you're hanging out in quadrant I, up in the top right. If x is negative but y is positive, you slide over to quadrant 2 in the top left. If both are negative, you drop down to the bottom left, quadrant 3. And finally, if x is positive but y is negative, you're down in the bottom right, quadrant IV.
Which brings us to Part 4, Accessibility and Distance. Let's see how this geometry builds the actual foundation for accessible architecture.
What I find absolutely brilliant about Shalini's map is how she placed the bottom left corner of Regien's room dead center on the origin, right on that 0, 0 mark. By doing this, she essentially turned the left wall of his room into the y-axis and the bottom wall into the x-axis. This means every single piece of furniture is chilling in quadrant 1, making all the measurements nice, easy, positive numbers.
You see, coordinate geometry isn't just about plotting random points on graph paper for a math test. It's an incredibly practical tool. By finding the distance between two coordinate points, we can measure actual physical gaps in the real world, like the width of a door frame. This is the exact math architects use to ensure a building's design is welcoming and fully accessible for people using wheelchairs.
Okay, Part 5, Coordinate Geometry Quiz. Let's put our skills to the test with 5 quick, real-world questions based on Rian's room. Let's see if this space is truly accessible. Question 1. Thinking back to those mapped axes, we need to figure out the horizontal distance from the y-axis all the way over to the start of the door, which is labeled as point D1. Any guesses? Well, if we trace it straight down, point D1 aligns perfectly with the number 8 on the x-axis. And since Shalini's scale is 1 unit to 1 foot, that means the door is exactly 8 feet away from the left wall. All right, question 2. Keeping that distance in mind, what are the exact coordinates of point D1? Think about the rules we just went over. If a point is sitting flat on that horizontal x-axis, what happens to its y-coordinate? Exactly, because the point lies flat on the x-axis, there's absolutely no vertical distance. It hasn't moved up or down from the starting line at all. So the x-coordinate is 8 and the y-coordinate is just 0, making D1 8, 0. Moving right along to question 3. If the door frame ends at point R1, which is at 11.50, how wide is the main room door? To find the physical distance between 2 points on the exact same axis, we use a super simple trick. We just subtract the smaller coordinate from the larger one.
So, by taking the end of the door at 11.5 and subtracting the start of the door at 8, we find out the room door is exactly 3.5 feet wide. Structurally speaking, a 3.5-foot door is generally a really comfortable width, which means a wheelchair user could enter Rian's room with 0 issues.
Okay, question 4. Let's look at a different doorway. The bathroom door coordinates are B1 at 0, 1.5, and B2 at 0, 4. So is it wider or narrower than the room door? This time, our points are living entirely on the vertical y-axis, the left wall. To find the width, we just subtract 1.5 from 4.
And that gives us 2.5. So the bathroom door is only 2.5 feet wide. Comparing the two, the bathroom door is significantly narrower than the main room door. In real-world architectural terms, 2.5 feet is honestly quite a tight squeeze, and it might actually need a design change to be fully accessible for a wheelchair user.
You all crushed those 4, so here is your 5th and final question. Something for you to think about. Look around the room you are sitting in right now. Where would you place the origin? How would you plot your bed, your desk, your doorway on a coordinate grid to guarantee your space is perfectly accessible for anyone who comes to visit? The next time you walk through a door, I want you to remember those ancient city grids, the stars above, and the incredibly beautiful math that makes sure everyone can navigate our modern world safely. Thanks so much for joining me for this explainer. Keep exploring, and I'll catch you next time.